Okay, so if you're prepping for, those senior level software engineer interviews like I am, how important it is to really understand how data is handled efficiently, especially, indexing.
Absolutely.
Right, and today we're going deep on this, the real workhorse behind it all, right? The B tree.
Yeah.
So this isn't just, cramming for interview questions. This is like foundational stuff,
Right.
for building any kind of complex system, right?
Yeah, you got it. This is not some obscure academic
Hmm.
topic or anything. This data structure we're going to look at, it's like the foundation for most relational databases and even a lot of the non-relational ones too.
Right, exactly. And I mean, if you want to land that senior role, understanding how these systems can just retrieve data so fast, it's crucial.
It's a must-have.
Yeah, absolutely. So our mission today is pretty clear, right? We really want to nail down like the core principles behind B trees,
Yeah.
the structure, how they do your magic with lookups, insertions, deletions, all that. And of course, we want to understand those trade-offs, the good, the bad, the ugly.
Right, the whole pic.
So by the end of this, we'll both have like a really solid mental model of how this thing works.
Exactly.
So where do we even begin with B trees? Like, what's a good starting point for understanding?
Well, I think a good place to start is to think about them as like an evolution.
Mm-hmm.
You're probably already familiar with like balanced search trees, maybe even binary search trees specifically.
Right, sure.
B trees. They build upon that same core idea, but there's a key difference, and it's this concept called fan-out.
Fan out. Okay, that sounds pretty technical. So what does that mean exactly for a B tree?
Basically, fan-out, it just refers to the number of children that a single node in the tree can have. So, in a binary search tree, each node has at most 2 children.
Right. Yeah.
But with B trees, a single node can have dozens or even hundreds of children.
Oh, wow. Okay.
And that's the secret sauce for making them perform so well on disk. You see, instead of going down many levels like in a binary tree, we can jump across huge amounts of data in each step.
Right. I see.
Fewer steps means fewer slow disk operations.
Yeah.
And that high fan out, it leads to a much shallower tree,
Huh?
especially when you have a ton of data.
Okay, that makes sense. So fewer levels to dig through means faster access.
Exactly.
Now, I remember you mentioned an analogy earlier about a library catalog.
Oh, yeah.
That helped me visualize this whole thing. Can you explain that?
Sure. So imagine you're in a library with one of those massive catalog rooms, those old card catalogs.
Yeah.
To find a specific card, first you have to find the right cabinet, then the correct shelf within the cabinet, then the drawer, and finally you can browse the cards in that drawer.
Right.
A B tree, it works in a similar way. It creates this hierarchy that lets you quickly navigate and find the info you need by narrowing down the search at each level.
Oh, okay, I get it. Like each step gets you closer to the exact piece of data.
Exactly.
So within each of these B tree nodes, how is the data actually organized to allow for this fast searching?
Well, inside each node, the keys, they're stored in sorted order. Now, this might seem simple, but it's super powerful because it lets us use really efficient algorithms like binary search within each node. So we can quickly find a specific key or figure out which child pointer to follow next. And that's why lookups in B trees have that logarithmic time complexity.
Right, logarithmic complexity. That's what we want for large data sets, right? It's like the sweet spot.
Exactly. It means the time it takes to find something grows much slower than the size of the data itself.
Now, you had a pretty good example about how many comparisons you need, even with billions of items.
Oh, yeah. So let's say you're looking for a specific key in a data set with like 4 billion records. With a B tree, you could probably find it in about 32 comparisons.
Wow, 32.
Yeah, think about that. If each comparison required a separate trip to the disk, it would take forever.
Right, it would be so slow.
But here's the thing. B tree nodes, they're designed to hold lots of items, potentially dozens, even hundreds of keys, and their pointers. So for each level of the tree, we only need to do one disk seek.
Right, so that's a huge optimization for systems that rely on slower storage, like hard drive. So we have these nodes with all these sorted keys and pointers. What's the overall structure of the tree? Is it just flat, or is there a hierarchy?
No, there's definitely a hierarchy.
Yeah.
At the top, you have the root node. That's your entry point.
Right.
Below the root, you have internal nodes. They're like the middle managers. They just guide your search down the right path.
Okay.
And finally, at the bottom, you have the leaf nodes. That's where the actual data you're looking for lives, or at least in some cases, pointers to the data.
Okay.
And between the root and the leaves, you can have multiple layers of these internal nodes.
I see. So it's like that library catalog analogy, right?
Exactly like that.
Now, another thing I remember you mentioning is that when we talk about how B trees are actually stored on disk, the terms node and page are often used interchangeably.
Yeah, that's right.
Yeah.
Because essentially B-trees are a way of organizing these fixed-size blocks of data, which we call pages.
Okay, so node page, same thing in this
Pretty
context.
much, yeah.
You also talked about fan out again and how it leads to a shallower tree. How does this relate to keeping the tree balanced and efficient as we add and remove data?
Right. So the fan out, remember that's the number of keys and pointers a node can hold. It's super important for balance.
Okay.
A higher fan out means each node can cover a wider range of keys.
Right.
So even with lots of data, the tree stays relatively shallow. And that's what keeps those structural changes like splits and merges, when we add or remove stuff, manageable.
So it helps to spread the workload out.
Exactly.
Now, we keep saying B tree, but you mentioned there might be a more specific term for the type of B tree we see in databases.
Yeah, that's right. The term B-tree, it's often used generally,
Yeah.
but the kind that's mostly used in databases, and the one we've been talking about, it's technically called a B+ tree.
B plus a tree. Okay. So what's the main difference between a regular B tree and this B plus tree?
The key difference is where the actual data records are stored. In a pure B tree, you can have data associated with keys at any level, even the root. But in a B+ tree, the data records, they're only in the leaf nodes.
I see.
So the internal nodes in a B+ tree, they just act as an index. They contain what we call separator keys, which are basically like signposts.
Right.
They guide the search down to the correct leaf node. That's what the actual data is.
Got it. So the internal nodes, they're just for navigation.
Exactly. And this design means that most operations that involve actually retrieving or changing data, they happen primarily at the leaf nodes.
Okay, that makes sense. So these separator keys, they're like the unsung heroes here. How do they actually work to help us navigate?
Yeah, they're essential. Think of them like guideposts in our library catalog analogy. Remember,
Yeah.
inside each internal node, these separator keys, they're stored in a specific order, sorted, of course.
Okay.
And each separator key, it divides the tree into subtrees. All the keys in the subtree to the left are less than the separator key, and all the keys to the right are greater.
I see. So it's like they define the boundaries.
Right. When you search for a key, you do a binary search within the node to find the range where your target key falls.
Okay.
The pointer associated with that range tells you where to go next, narrowing down your search.
So each level you go down, you're getting closer and closer?
Exactly.
Now, you mentioned that B trees grow in a bottom-up way, unlike binary search trees, which grow top-down. Can you explain that a bit more?
Sure. So in a typical binary search tree, you start at the root and add new nodes by comparing them and placing them in the left or right subtree.
Okay.
But with B trees, new data is always added to a leaf node. If that leaf gets full, it splits, and the middle key gets promoted up to the parent.
Right.
And this can continue all the way up the tree, sometimes even causing the root to split. And that's the only way the height of the B tree actually increases.
I see.
Another interesting thing is that B trees, they like to keep their nodes at a certain level of fullness. This means there might be some empty space in the nodes. So sometimes storage utilization can be around 50%, but it's usually higher in practice. And the important thing is that this doesn't really affect the performance.
That's good to know. So it's like a trade-off between storage space and speed.
Yeah, exactly.
Okay. So we have a good idea of the structure now. Let's talk about how we actually use a B tree. What's the process for looking up a specific key?
Okay, so for lookups, it's pretty straightforward. You start at the root node and you basically follow a path down to a leaf node.
Okay.
So like we talked about, you use the separator keys in each node to figure out which child pointer to follow. You keep doing this level by level until you hit a leaf.
Right.
At the leaf node, you do a search for your target key. If it's there, great. If not, the key's not in the tree.
So it's like a process of elimination at each level.
Precisely.
And you mentioned that the time complexity for this lookup is logarithmic. Can you explain why that's so important, especially with large data sets?
Sure. Think about it this way. At each level of the B tree, you're basically eliminating a huge chunk of the data from your search. Because of the high fan out, if a node has, say, 100 children, by going down one level, you've narrowed your search down to just one of those 100 subtrees.
Okay, that makes sense.
So you're cutting down the possibilities really fast. That's what gives us that logarithmic performance. You can think of it in terms of disk accesses. The height of the tree is roughly proportional to the number of disk accesses you need.
So the shallower the tree, the faster the search?
Exactly.
Yeah.
And because of the high fan out, the height grows very slowly,
Okay.
even with huge data sets.
Okay.
So the overall lookup complexity is O log n, where n is the number of keys.
O log n. Got it. Now, what happens when we want to add new data to the B tree? How do insertions work, and what are these splits you mentioned?
Right, so when you insert a new key value pair, you first need to find the right leaf node where it should go. You do this using the same lookup process we just talked about.
Okay.
Once you find the leaf, you try to insert the new key.
Okay.
But if the leaf node is already full, then we have a problem.
Right, because it can't fit any more data.
Exactly. This is called an overflow. And to maintain the B-tree's properties, we have to split the node into two.
Okay, so walk me through this splitting process. What actually happens when a leaf node needs to be split?
Imagine a leaf node that's full. It has the maximum number of keys. Let's say n keys.
Okay.
Now you try to insert another key, so we have n plus 1 keys, and it's too much.
Overflow.
Exactly.
Yeah.
To fix this, we create a new empty leaf node. Then we move about half of the keys from the original node to this new node, keeping them sorted, of course.
Yeah.
The key that's right in the middle after you add the new key that becomes the split point,
Okay.
that middle key gets promoted up to the parent node.
So it goes up a level.
Exactly.
Yeah.
And in the parent node, that promoted key acts as a new separator. It divides the range of keys that the original leaf node used to cover.
Okay. I see.
And the parent node also gets a new pointer that points to the new leaf node we just created.
So the parent node is keeping track of everything.
Exactly.
What happens if the parent node is also full when we try to promote this new key?
That's when things get interesting. If the parent node is full and can't take the new key and pointer, then it has to split as well.
So it's like a chain reaction.
Exactly. This splitting can go all the way up the tree, potentially even splitting the root node.
And what happens then?
If the root splits, we create a brand new root node. That new root will have just the promoted key from the old root and 2 pointers, one to each of the new child nodes that came from the old root.
Okay, so that's the only way the whole tree gets taller.
Exactly. It's how the B tree stays balanced, even as we add more and more data.
Now we talk about how leaf nodes split. Is it different for the internal nodes?
Yeah, there are some differences, but the basic idea is the same. You split the node and promote a key up to the parent.
Okay.
But with non-leaf nodes, the split usually happens because a split happened at a lower level.
Like in a leaf node.
Yeah, exactly. So we need to add a new child pointer to the non-leaf node. But if the node is full, then it has to split.
So like a domino effect.
Yeah, kind of. So we create a new non-leaf node move about half the pointers and keys to the new node, and then promote the middle key up to the parent.
Okay.
And it's important to remember that the key being promoted isn't necessarily the key we originally tried to insert. It's just a key that divides the ranges covered by the child pointers.
Right, because the internal nodes are all about guiding the search.
Exactly.
Now let's talk about deletions. What happens when we remove a key from the B tree, and how do merges work?
When you delete a key, you first find the leaf node where that key is. Once you remove the key, the node might become underfull.
Underfull.
Yeah, it means it has less than a certain number of keys. This can make the tree less efficient. So to fix this, we sometimes do a merge operation.
A merge.
Yeah, we combine the underfull node with one of its siblings.
Okay. So how does a leaf node merge work?
So imagine a leaf node that's underfull after we delete a key,
Okay.
and it has a sibling next to it. If the total number of keys in both nodes is less than the maximum capacity of a node, then we can merge them. So we combine all the keys from both nodes into one. The separator key from the parent node that was between them that gets moved down into the merged node, and the empty sibling node is removed.
So we're basically cleaning up the tree.
Right, exactly. And the parent node loses its pointer to that empty node as well.
So it's all about keeping things tidy and efficient.
Exactly.
Now, how about merging non-leaf nodes? Is it similar to merging leaf nodes?
It's similar, but we also have to deal with the child pointers. When you merge two non-leaf nodes, you combine all the keys in the separator key from the parent. But you also have to redistribute the child pointers from both original nodes.
Okay.
You have to make sure they're still pointing to the correct ranges of keys.
Right, because it all has to stay connected.
Exactly.
Yeah.
And this kind of merge in a non-leaf node, it usually happens after a pointer deletion that came from a lower level in the tree, like after a leaf node merge.
I see. So it's like a ripple effect. So splits make the tree grow and merges make it shrink. Are there any other techniques that B trees use to manage their structure and maybe avoid all these splits and merges?
Yeah, there's something called rebalancing or redistribution.
Rebalancing.
Yeah, instead of doing a split or merge right away, the B tree tries to redistribute keys between sibling nodes.
Okay.
So for example, if a sibling node has a lot more keys than it needs, we can move some of those keys to the underfull node.
Right.
And then adjust the separator key in the parent node. This can help prevent those more complex splits and merges.
So it's like a way of proactively balancing the tree.
Exactly.
Okay, so we've talked a lot about B trees specifically. Let's zoom out a bit and see how they fit in with other data structures. We saw that comparison with binary trees and 2-3 trees. What were the key takeaways from that?
That comparison shows how we've evolved towards data structures that work really well for disk-based systems. Now, binary search trees, they're simple, but they can become unbalanced really easily. And that can lead to really bad performance for large data sets.
Right, linear time complexity, which is a nightmare.
Exactly. So then came 2-3 trees. They stay balanced by letting nodes have 2 or 3 children.
Okay.
But B trees, they take this idea even further. By allowing a much larger number of children per node, the high fan-out we talked about, they can create a really shallow tree. And that's super important for minimizing disk I/O.
Right, because accessing the disk is slow.
Exactly. So while binary trees might work okay for small data sets or for data in memory B trees, they're designed specifically for performance when the data's on disk.
Okay, so the right tool for the right job.
That's it.
Now, you mentioned another way of looking at binary trees. What was the point you wanted to make with that?
I wanted to emphasize that both binary search trees and B trees, they use keys to divide the data into subtrees with specific ranges of keys.
Okay.
That's the core idea behind how they search so efficiently. Doesn't matter how many children each node can have, that principle is the same.
It's all about dividing and conquering.
Exactly.
And what about that diagram showing the B-tree hierarchy? What was the main thing to take away from that?
The main point was to show how the search gets more and more refined as you go down the tree. The root node gives you a general overview. Then the internal nodes give you more detail. And finally, you get to the leaf nodes where the actual data is.
Right, it's like zooming in on a map.
Exactly.
And another interesting thing is that in a lot of B-tree implementations, the leaf nodes are linked together.
Oh yeah, that's right. They form a linked list. And that's really important for doing range scans across the data.
Oh, I see. So you can easily scan through a range of keys without jumping all over the disk.
Exactly. It's a big performance boost.
So B-trees aren't just some theoretical concept. They're actually used in real systems all the time, right?
Oh yeah, they're everywhere. They're like the foundation for almost all relational databases, like MySQL, PostgreSQL, Oracle, SQL Server, you name it.
Wow.
And even a lot of NoSQL databases use them too. They've been around for decades, and they're still the go-to solution for managing large amounts of data.
So they're tried and true. Now, you compared B-trees to SSTables, saying they both keep things sorted but have different designs. Can you elaborate on that?
Sure. So both B trees and SSTables, they're about keeping key value pairs sorted for efficient lookups. But how they manage that data on disk is different.
Okay.
B trees work with these fixed size pages, and they update data in place. So if you change something, you modify the existing page.
Okay.
But log-structured systems like the ones that use SSTables, they write data in a sequential append-only way. So they create these immutable segments that are sorted and written to disk.
So it's a different approach to handling changes.
Exactly.
Yeah.
And it leads to different performance characteristics and trade-offs.
Right. Different tools for different jobs.
Exactly.
But you had an example of using a B-tree index to look up a user id in a database. Can you walk us through that?
Sure. Let's say you have a database table with user information.
Yeah.
And you need to find users by their user id.
Okay.
You create a B-tree index on that user id column. Now, when you search for a specific user id, like 251, the database uses the index. It starts at the root node and compares the target user id with the separator keys.
Okay.
Based on those comparisons, it follows the right pointer down to a child node.
Okay.
It keeps doing this until it gets to a leaf node.
Right.
That leaf node will contain the target user id and a pointer to the actual row in the main data table where all the user's information is stored.
So the index leads you right to the data.
Exactly.
And what happens when you add new data to the table? Like you had that example with inserting a user with user at 334.
When you insert a new key, the B-tree index needs to be updated. So it finds the right leaf page where the new key should go. If that page is full, it splits.
Like we talked about before.
Yeah, exactly.
Mm-hmm.
The data is divided into 2 pages, and the middle key gets promoted to the parent page.
Right.
So the index stays balanced, and you can still search it efficiently.
Okay, that makes sense. Now, these B-trees, they've been around for a while. How do they ensure data integrity and durability, especially when things like crashes happen? You mentioned write-ahead logs.
Data reliability is super important. So B-trees use mechanisms like write-ahead logs, or WAL for short.
WAL.
Yeah, basically, before making any changes to the data on disk, the B-tree first writes a record of that change to the WAL.
So it's like a safety net.
Exactly. The WAL is append, so writing to it is very fast. If the database crashes before the changes are written to the actual B-tree pages, the WAL can be used to recover.
So it can replay the changes and get back to a consistent state.
Exactly. It's like a journal of what happened.
Okay, that's clever. Now, are there any common optimizations that are used with B-trees to make them even better?
Oh yeah, there are lots of them. One common one is copy on write.
Copy on write.
Yeah, instead of overwriting a page when it's changed, you create a new copy with the changes and then update the parent pointers to point to the new copy.
Oh, I see.
This can help with performance and concurrency. Another optimization is key abbreviation, where you only store part of the key in the internal nodes to save space. And a lot of systems, they try to store the leaf pages sequentially on disk. This is great for range scans because you can read multiple pages with one disk operation.
So it's all about minimizing those expensive disk accesses.
Exactly.
Okay, so lastly, let's talk about B-trees versus LSM-trees again. You mentioned they have different strengths and weaknesses. Can you give us a simple rule of thumb for when to choose one over the other?
Generally speaking, LSM-Trees, they're really good for write-heavy workloads. They can write data sequentially, which is fast, and they can be good at handling write amplification in some cases.
Okay.
But B-trees, they're usually better for read-heavy workloads because the data is organized in a way that makes it easy to find without having to check multiple places like you might in an LSM tree.
Right, so it depends on how much reading versus writing you're doing.
Exactly. But you always have to consider the specific workload, the data, the hardware. Everything matters.
So benchmarking is key.
Absolutely. You can't just assume one is always better.
And write amplification, it's still something to think about with both types, right?
Yeah, it's always a factor. But it works differently. In each case, B-trees do in-place writes, while LSM trees use sequential writes and background compaction, which can also cause write amplification.
Right, so it's a trade-off.
Yeah. And another important thing is that in a B-tree, each key only exists in one place. This makes it easier to do things like locking for transactions.
Oh, I see. So if you need strong consistency guarantees, B-trees might be a better choice.
They can be, yeah.
Okay, so this has been a really deep dive into B-trees. We've covered a lot of ground. We talked about the structure, the fan-out, the logarithmic complexity, the splits and merges, all that stuff.
Yeah, we've gone through a lot.
And for anyone preparing for a senior software engineer interview, this is essential knowledge.
Absolutely. Understanding B-trees shows that you get how data is stored and retrieved efficiently, which is key for senior level roles.
So to wrap up, here's something to think about. Given everything we've discussed about B-trees and LSM trees, what specific real-world workloads would make one a clear winner over the other? Think about the read-write ratio, the data size, the consistency requirements, all that good stuff.
It's a great question to ponder.
Yeah, definitely. Well, that's it for this deep dive. We'll catch you next time for another fascinating topic in the world of tech.
See you then.
Bye.